All right, well, I will begin with a word of prayer. So, dear Father, we thank you for this day. Again, I thank you for this class and this weekend just completed. Help us to glorify you what we do this morning. Lord, in your name I pray, Lord Jesus. Amen. Let's see here. So, let me see if I can get the top hat up. My computer will work. Do you guys have any questions while I'm messing around with this? So today we're talking about coordinate vectors and how to change from one coordinate system to another. So first of all, of course, we're going to have to, review a little bit how we calculated the coordinate vector. And I'm going to start with column vectors, and then we'll work our way towards more interesting cases. Although the case that's of most importance to us, of course, is the column vector case. So, and I think today I'm going to use notation, at least to start with. I'm going to use primes and bars. Now, physicists like to do this kind of thing. They'll take a letter to denote a particular variable, and then to use different coordinate systems, they'll add some kind of like a prime or a bar or something, so that you've got the same letter for the object in all the different coordinate systems, and you're just kind of using some other notation to keep track of which coordinate system you're in. So coordinate change is what we're talking about today. We'll start with vectors. Next class, we'll talk about the more daunting task of coordinate change for linear transformations. So here we go. Consider V equals to Rn with basis beta prime. So we've got V1 prime, V2 prime, Vn prime. So that's one basis. And another basis, beta bar, and I'll just use V1 bar, V2 bar, Vn bar for that other basis, all right? So if x is a element of Rn, then we define the coordinate vector of x with respect to beta prime to be like x1 prime, x2 prime, xn prime, and the coordinate vector of x with respect to beta bar will be x bar 1, x bar 2, x bar n. At least this notation will get us started, and we'll drift away from it as class goes on, all right? So you guys tell me, what's this mean then? We have, on the one hand, we have x is equal to, let's see here, x1 prime, v1 prime, plus x2 prime, v2 prime, plus xn prime, vn prime, right? That's what it means to say that the coordinate vector is x1 prime, x2 prime, all the way out through xn prime, right? It means that you can build the given vector, in this case x, as a linear combination of the bases in that way, right? And of course, we also have x is equal to x bar 1, v bar 1, all the way on out to x bar n, v bar n, right? Now, both of these we can repackage as a matrix calculation, right? Remember that we have here, we can write x is equal to the matrix v1 prime, v2 prime, vn prime, times the vector x1 prime, x2 prime, all the way on down, xn prime. And then over here, we can likewise write x is equal to the matrix v bar 1, v bar 2, all the way out to v bar n times the coordinate vector x1 bar, x2 bar, xn bar, right? So like notationally, what's going on here? We've got x is equal to, on the one hand, the beta prime matrix times the beta coordinate vector of x, beta prime coordinate vector of x, right? And on the flip side, we've also got x is equal to the beta bar coordinate matrix, right, times the coordinate vector of x with respect to the barred coordinate system. So this is, you're like, well, why don't you just do it once? I mean, I figure if I do it twice, you're twice as likely to get it, I guess, maybe, right? So it's the same argument, just two different notations, yeah? So my question to you then is, how are the coordinate vectors with respect to the different bases related? How can we meet in the middle, so to speak? Why don't we just, x is equal to x, right? So we have, obviously, this equation that beta prime matrix times the coordinate vector of x with respect to beta prime is equal to the beta bar matrix, right, times the coordinate vector of x with respect to beta bar. So if I want to solve for the coordinate vector, let's say with respect to the barred basis, x bar, then I just multiply by the inverse of the basis matrix, the right one, beta bar, inverse of beta bar matrix. I multiply that times the beta prime matrix times x beta prime. And there you go. That's how the coordinates are related. If we go from beta prime to beta bar, we have to multiply by that matrix. So this right here is what you would call the change of basis matrix, or change of coordinate matrix, you could say. All right. What would the relation be if we were going, say, from beta prime? If I wanted to start with, say, the barred coordinates and go to the other one, how would that? What's the formula there? A little different, right? What's the difference? We have to do the inverse of the prime matrix, right? And then multiply by what? The beta bar matrix. Okay? So example 1, let's look at x equal to, 1, 2, 3, 4. And we'll look at the basis beta prime equal to E4, E3, E2, E1, all right? And let's make our beta bar matrix more exciting. There we'll do like E1 plus E2, E1 minus E2, E3 plus E4, and E3 minus E4. That should be a little bit more exciting. So these are two different bases for four-dimensional space, right? Yeah? So like, we can just go ahead and write down, x is equal to what? It's equal to E1 plus 2E2 plus 3e3 plus 4e4, right? That's what I get from this directly. That's what the standard basis is. 1 of e1, 2 of e2, 3 of e3, 4 of e4. So in order to see the coordinate vector with respect to this basis, I just have to think about this like this. I have 4 of e4s, I have 3 e3s, I have 2 e2s, and I have 1 e1s. Right? So therefore, the coordinate vector of x with respect to the beta prime basis is simply 4, 3, 2, 1. All right. Now suppose I want to calculate the coordinate vector with respect to the beta bar basis. Well, we can try to use the coordinate change formula. Which one do I want to use? Do I want to use this formula here? Or do I want to use that formula there? Which one do I want to use? Given the work we've already done here on the board. 50-50. You got two choices. I think we want to use that one, right? Because we've already got this, right? But that's 4, 3, 2, 1, and we can figure out what these matrices are. Okay, so here we go. X beta bar, it's going to be, according to that over there, we got to take the beta bar matrix, we invert that, we multiply by the beta prime matrix, and we multiply by, of course, the coordinate vector of x with respect to the beta prime coordinates. That's the rule. The question then is, can we do that inverse? So let's write it out. We've got 1, 1, 0, 0, 1, minus 1, 0, 0, 0, 0, sound effects optional, 1, 1, 0, 0, 1, minus 1, like so. Then you got this here, you got to invert that thing. The beta prime matrix is simply E4, E3, so that's 0, 0, 0, 1, 1, 1, 1, like that. All right. And of course this was 4, 3, 2, 1. So can you invert that? It's a 4 by 4 matrix, but can we invert it without doing some sort of ginormous row reduction? I think we can, right? What do you do? Yeah, so this is a block diagonal matrix, so we just invert the blocks. Very good. So we've just got, looks like minus 1/2, minus 1, 1, minus is on the off diagonal. It's the same inverse both places, isn't it? And I'm just going to do this multiplication over there. What's that multiplication? What do you get here? Which is totally unsurprising, really. What did we say before this derivation? We said x is equal to, among other things, beta prime times x beta prime, right? So when I multiply these, what do I get back? I just get back x again, right? Which is 1, 2, 3, 4. All right, so then we've got, I'm going to pull the half out front, if you guys don't mind. So I've got a half, and I've got myself a 1, 1, 1, minus 1. 1, 1, 1, minus 1 times 1, 2, 3, 4. All right, so what we get is 1/2 of, let's see here, 1 plus 2 is 3. 1 minus 2 is what? Minus 1? 1 minus 2? Yeah. And then we've got like 3 plus 4 is 7. 3 minus 4 is minus 1. So if you like, our coordinate vector is 3 halves minus 1 half, 7 halves minus 1 half. That's the coordinate vector with respect to the beta bar basis. Now we can check our answer, right? Let's try checking our answer. So allegedly, the coordinate vector is 3 halves minus 1 half, right? So if we do 3 halves of my first thing, which was E1 plus E2, right, minus 7 halves, my bad, minus 1 half of E1 minus E2, right, plus 7 halves of E3 plus E4, minus 1 half of E3 minus E4, what happens? We've got like 3 halves, 0, 0, right? Plus like 1 half, minus 1 half rather, plus 1 half, 0, 0, plus 0, 0, like 7 halves, plus 0, 0, minus 1 half, 1 half. And what happens when you add these?
You get 1, 2, 3, 4.
1, 2, 3, 4, which is what we have to get, right? If that actually is the coordinate vector of x with respect to the beta bar basis, that has to be what it works out to, right? That's the meaning of coordinate vector, is that when you take a linear combination of the basis, you get back to the basis for which that is the coordinate vector. Any questions? So I think if you have everything in front of you, like if you actually explicitly have both bases in all this, in some sense, this calculation is kind of silly, right? Because you could easily just separately calculate this, right, and that, and that. You could just separately calculate these, right? You don't have to go from one to the other with the matrix multiplication, but it's important to know about the possibility that we can do that, all right? So this is coordinate change for column vectors. Now, let me show you guys how this goes for abstract vector spaces. It's a little bit more complicated because for an abstract vector space, we can't just make this basis matrix thing that we did, right? Like the basis matrix is, oopsie doopsies. Oh man. Sorry, people not here. Well, they're not watching anyway, but I'm just kidding, they're watching. Are they watching? I don't know. They're watching. Mm-hmm. I have this like cycle of, I don't know, maybe it's a cycle of apathy. I'm not sure what it is, but like I go one semester, I have a bunch of quizzes because I'd be like, people don't pay attention unless you have quizzes. And then I have another semester like, enough of quizzes. The quizzes are too like horrible. I can't do quizzes all the time. And then I'm reminded people don't pay attention unless you have quizzes. And so I go back and forth and back and forth. But you're currently in the no quiz semester. Are you enjoying it? Yeah, okay. All right, so suppose we have, oopsie doopsies, two different, oh man, that that purple marker wants to stain the board. Let's see here. Suppose we have two different bases, and I'll keep using the same notation, all right, for a given abstract vector space. Everything here is finite dimensional. I don't know how to write down the matrix of a vector in an infinite dimensional context, even in the next course. That's not something I can, well, okay, that's not entirely true. There is actually a concept of coordinate vector in infinite dimensions, but it comes at considerable theoretical cost, and as far as I know, I don't have an interesting calculation for it. Anyway, so suppose we have, again, a matrix beta, a basis beta prime, and beta bar, All right. So we've got vector space V up here. Right? So I've got some point up here, X. This is trash. Oh well, too much. And on the one hand, I've got, let's say, phi beta prime. And on the other hand, I've got phi beta bar. So here, again, beta prime is V1 prime, Vn prime. And here beta bar is V1 bar, Vn bar. But this time I'm not assuming that they're column vectors. All right? So like the top box could be a set of polynomials for us or a set of matrices. Okay? Well then, remember we talked about, we define phi beta prime, sideways TIE fighter prime of x is equal to the coordinate vector of x with respect to beta prime. On the other hand, sideways TIE fighter beta bar of x is equal to the coordinate vector of x with respect to beta bar. All right? So that gives me an honest to goodness n vector down here and an honest to goodness n vector over here. Oopsie. Gotta watch out. If I flip the bars and the primes, everything will descend into chaos. All right. The question then is, how do you get from one picture to another, right? These are two different snapshots of this abstract vector space. We're taking the abstract vector space and replacing it with n-dimensional column vectors. The reason we do that, of course, is because once we're with column vectors, then we can calculate like we've already done in this class, right? All those row reductions and stuff happen for us. But, so here's the deal. To get from there to there, what I do is I think about traveling the following path. Like that. So that is actually the first shall be last and the last shall be first. So the last thing is phi beta bar. But the first thing is phi beta prime inverse. And so like, let me write this out for you. So we have x beta bar, we can write as phi beta bar of x, right? But if you use your imagination, you can also write that as phi beta prime. Oh, my bad. You can write that as phi beta bar composed with phi beta prime inverse composed with phi beta prime of x. So what I've done is I've just inserted a copy of the identity map, which you can do without changing anything, because the identity map, this is just the identity map on V. All right. And, okay, so then that is literally phi beta bar composed with phi beta prime inverse, that map of phi beta prime of x, right? But that is phi beta bar composed with phi beta prime inverse acting on x beta prime. But look, the matrix which I'm about to underline in this hideous Carolina blue, right? That is, well, I should probably use purple since I already did. That's the purple line, right? That is a what? A mapping from what to what? It's a mapping from Rn to Rn, all right? And in fact, it's a linear mapping. It's a linear transformation. And therefore, we can actually further simplify this formula a bit. A lot of people like to look at the coordinate change for vectors formula. Oh, getting in my eyes. Not good. Not good. Let's see here. All right, so we have the coordinate change, coordinate vector, the beta bar coordinate vector of x is equal to apparently phi beta bar composed with phi beta prime inverse, and that it takes as its input the coordinate vector with respect to the prime system. But this is a linear transformation, which means we can write that as a standard matrix. See, that's really just the standard matrix of beta bar composed with phi beta prime inverse matrix multiplying the coordinate vector. Because it's a linear map on Rn, we can write it in terms of a standard matrix multiplication. And what can we find a formula for that standard matrix? Like, I know this is like a little bit scary, but we can make it more concrete. Like, how do we find the standard matrix? What is it? We're supposed to do what? Phi beta bar of phi beta prime inverse of what? To get the first column, we feed it E1, right? And then we keep doing that until we get to the nth column, right? You guys, you guys are so quiet. I can't tell if you're completely lost or what. Like, that's the standard matrix of T, right? I'm just applying that idea to the case that T is equal to the composite of these coordinate maps and their inverse. Right. Now, let me point out something else here. We have, by definition, phi beta prime of V1 prime is what? What's phi beta prime of V2 prime? What's that? For example, V1 prime, how do we get it as a linear combination of V1s? It's 1 times V1 prime, right? Plus 0 times V2 prime plus 0 times Vn prime, right? What are the coordinate vectors? What's the coordinate vectors then of V1 prime? It's 1, 0, 0, 0, 0, 0. In other words, the coordinate vector of V1 prime is E1. The coordinate vector of V1 prime is E1. What's the coordinate vector of V2 prime? E2, right? The same calculation. You put a 1 here and zeros elsewhere. And this goes on, all right? Like, generically speaking, phi beta prime of, let's say, Vj prime is equal to Ej. So if you understand this, what does that say about phi beta prime inverse of Ej? What should that be equal to? This is an invertible map, which means that you can hit both sides with the inverse. What happens when you compose with the inverse? You get back where you started, right? But this immediately gives us that phi beta prime inverse of Ej is equal to Vj prime. So, and this is something worth remembering. The coordinate vector map is a way of converting the abstract basis that you're given to the standard basis in exactly the same order. And the inverse to the coordinate map can be understood as simply the machine which converts the standard basis in your coordinate vector formulation back to the abstract basis. That's what it does. So as you look at these, what we're actually looking at is simply phi beta bar of v1 prime, phi beta bar of v2 prime, all right, and so forth and so on. Finally, phi beta bar of vn prime, which if we go back to the other notation, what are those? We're talking about, and you'll see this formula oftentimes appears in books, v1 prime beta bar, v2 prime beta bar, vn prime the beta bar. In other words, this right here, so the change of basis, or change of coordinates, let's say matrix, is made from concatenating the coordinate vectors of one basis in terms, the coordinate vectors of one basis with respect to the other. Now, we can connect this discussion, right? We can look at the coordinate matrix of like phi beta bar composed with phi beta prime inverse, right? I'm telling you it's equal to v1 prime beta bar vn prime. Every so often Dr. Sprano gets loud over there. Let's see here. Something exciting happening. I think it's calculus 2. Where are they right now? Probably separation of variables maybe, integrating factor method, I don't know. So let us connect to these two worlds for a second here. See if we can get back to the formula we got to earlier today as an exercise in understanding all of the different notations here, right? Because understanding the notation actually is one of our bigger goals today. If v equals to Rn, then we can take this formula we just derived and try to get back where we started, right? So how do you find the coordinate? How do you find the coordinate vector? What's the formula in arbitrary, so if I just had phi beta bar of x in Rn, the formula, not beta bar, just beta, phi beta of Rx, I take the beta inverse matrix times x. That is the formula to calculate the coordinate vector for column vectors with respect to the basis beta. So if I use that here, I've got, beta bar inverse times v1 prime and beta bar inverse times vn prime. But then we can do the column by column matrix multiplication rule, and that's beta bar inverse, because it's everywhere, right? Times v1 prime, v2 prime, vn prime, all right? What is this? That's just the beta prime matrix, which is what we derived earlier today through more direct arguments, just using matrix multiplication by the inverse matrix, right? Now I've recovered that formula from a very different viewpoint, namely thinking diagrammatically about the coordinate maps as a means of replacing abstract vector space with Rn. Questions? So, one thing I should show you guys before I forget, and this is not currently in my handwritten notes for this lecture, but I think it's worth talking about for at least a second, which is there's one kind of coordinate system on n dimensions which makes things like way easier. So you see this at the moment. If we're talking about column vectors, right, the process of finding the coordinate vector is really quite troublesome for an abstract basis, because why? You have to do what? It's the inverse matrix problem, right? Like basically you're up against the problem of inverting an n by n matrix, which is generally kind of a pain. I mean, we can do it, right? But it's troublesome. There's one kind of basis which you don't actually have to do that for. Like the basis itself is so nice, it's so pretty, that the coordinate formulas just fall into place. And that's when we have what's called an orthonormal basis, right? So this is a larger topic later in the course, but it could afford some foreshadowing, so let me take 10 minutes and talk to you about it. So, definition, all right, let's say beta equals to V1, V2, Vn is an orthonormal basis if Vi dot Vj is Kronecker delta Ij. Now what that means is 1 if I is equal to j, and 0 if I is not equal to j. All right? And so there's a simple and beautiful theorem about how to calculate coordinates with respect to the orthonormal basis. And so here it is. Let's suppose that we have, x is equal to, I'll use a different letter just for the sake of, being weird. Okay, fine, I'll put bars on it. Bar, 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 bar. Be consistent with the rest of my lecture. Bar, bar, bars everywhere. So x is equal to the sum I equals 1 to n of x bar I, v bar I, all right? Check this out. If we take x dot v bar j, this is the dot product. We know the dot product, right? We've been doing dot products for like matrix multiplication ad nauseum. You guys know what the dot product is. Some of you are in Calc 3, so you know better, right? Then this is the sum, I equals 1 to n, of x bar I v bar I dot v bar j, using properties of the dot product to bring this dot product inside the summation, all right? But by assumption, this is an orthonormal basis. So the dot product of vi and vj is simply Kronecker delta ij. This Kronecker delta is the natural enemy of the finite sum. It's almost always 0, right? Except when it's not. Where is it not? It's not 0 just for I equal to j. So that sum, n minus 1 of those things are sent to 0. The only thing that remains is what? X bar what? J is free here, so we have to keep j, I equals to j, so we just get x bar j. That's it. So we have this theorem, which is ever so lovely, which says that the coordinate vector of x with respect to the orthonormal coordinate system is simply the vector of dot products of x. Oops. Which you can also rewrite as v1 bar, v2 bar, v bar n transpose times x. Oh, corollary. For beta orthonormal, the beta bar orthonormal, beta bar inverse is equal to what? I mean, this is still equal to, by our previous arguments, equal to beta bar inverse, right? Times x, but that's true for all x. Therefore, the transpose of the basis matrix is the inverse. Now that's kind of more of theoretical curiosity for us at the moment. But this idea that we can calculate coordinates simply by taking dot products, well, that's huge. If only we could always do it. We can't, because not every basis is orthonormal. Yeah? Let me see if I can conjure up a orthonormal basis off the top of my head right here, right quick. How about, what example am I on, guys? 2? All right. So here we go. Let's try beta bar, let's see, V1 bar, oh man. How about 1 over the square root of 3, 1, 1, 1. That's the drag, the downside of the, oops, that was almost, I still haven't hit a student that I know of. At least not directly, maybe off a ricochet, that maybe has happened. How about this, 1 over square root of 2, 1 minus 1, 0, right? Actually, I'm going to stop right there. We can talk about W equal to the span of V bar 1, V bar 2. This would be a two-dimensional subspace of R3, right? And then I could say, okay, so what are the coordinate vectors? If I take, for instance, x equal to, I don't know, 2, 0, 1, that's actually an element of W. Find the coordinate vector of x with respect to beta bar. Well, easy peasy. We just do x dot v1, and we do x dot v2 bar, rather. What are those? I get 3 over root 3, right? For that. Fine, I'll write it out. 2 over root 3 plus 1 over root 3, also known as, well, 3 over root 3, also known as root 3. X dot v2, on the other hand, is 2 over the square root of 2, plus 0 plus, well, 0. So we just get actually square root of 2. So therefore, the coordinate vector of x with respect to the beta bar basis, in this case, is simply square root of 3, square root of 2. Actually, this example, we couldn't use the basis matrix stuff to do, could we? Because it's not like the basis matrix formulas, the slick formulas, they only really work for what? When we're talking about Rn, right? If we're talking about a subspace of Rn, we almost have to go through sort of the diagrammatic idea to change coordinates, truth be told. So subspaces for coordinates are a little bit trickier than like the full space. I do have a couple of examples to show you guys. Listen, so I was thinking about, as I wrote the lecture for today, writing it out, I wrote it out in perhaps a more logical order, but I don't think it's like pedagogically like optimal. I think it's better for you guys to do what we did this morning, which is to look at column vectors to start with and focus most of our attention on column vectors. That said, the diagram that I wrote, and the abstract coordinate change I talked about, I don't think you can fully understand it without seeing a couple of examples. And for that reason, I've written 2 examples for you. One polynomial and one matrix. All right. So let's look at those. It won't take us but a second if I can get my email to work. And this is not actually lecture 1. It's just because I couldn't remember which lecture I'm on. So I'm in the process of still writing this thing up. Come on. What is it doing? All right, it's being funny. All right, so come on, you can do it. You can do it. I said you can do it. Are we done with the Olympics yet?
Yeah.
Okay, just checking. I don't really pay attention. The stuff ceremonies. Have they managed to not offend all of Christianity this time? I hope. That'd be good. So this basically is what we went through. Here's a lovely picture of the diagram. I think the one I wrote on the board's a little bit better. But anyway, we derive, that's the coordinate change theorem. So here I have an example where I have the regular monomial basis and then the reversed order monomial basis for cubic polynomials, right? Kind of silly. 1x, x squared, x cubed versus x cubed, x squared, x1. And then I'm looking at this particular polynomial, a plus bx plus cx squared plus dx cubed, and I want to compare the coordinate vectors with beta prime and beta bar. But I made myself go through the process of calculating the change of basis matrix, and it ends up being much like the example I did today, E4, E3, E2, E1, right? And on the flip side, of course, I can calculate the matrix of f of x with respect to the regular one is ABCD, whereas with the reversed one it's DCBA. But if I multiply DCBA times my change of basis matrix, I get ABCD, all is well in the world. All right, yay. Now, here's another example. I have, 2 by 2 matrices, and I decided to get out my symmetric / anti-symmetric basis again. So the first 3 are the symmetric part, and then you got the anti-symmetric part. And if I take the matrix A, I can express it, of course, in terms of the usual unit matrix basis with coordinate vector A, B, C, D. But then I can try to think about, well, what are the coordinates of that matrix with respect to the less standard basis that reflects the symmetric and anti-symmetric subspaces of the 2 by 2 matrices, right? And so I need to calculate this. I calculate the change of coordinate matrix. So I have to do this one. I did a little bit of sneaky business. It's obvious that E11 bar is just that, and it's obvious that E22 bar is just that because E11 and E22 are respectively the first and the second elements of beta bar. But these are not in beta bar. So what I had to do was I just did the standard symmetrization trick. So just basically adding 0. And once I do that, that's the third thing, and that's the fourth thing. That's the third thing, and that's minus the fourth thing. But of course, I got a division by 2. So that's why I put 1/2, 1/2, and 1/2 minus 1/2 here. And so lo and behold, I can multiply my coordinate vector with respect to the usual basis times this change of basis matrix. I get that. That's the coordinate vector of the matrix with respect to the beta bar matrix. And I can check my calculation. I can see that if I do take those as my weights for the linear combination, I reproduce ABCD as I ought to. All right. Yeah. And then I think at that point I shifted back to column vectors, which is what we've already done today. And I do have one other maybe example or two in here. I haven't yet written out the orthonormal one, so I'll try to add a page about that. But anyway, I think we're done for today. If you guys have questions about the homework next class, you should ask. We have time for questions if you got them.